I am Brent Komer, and I will be presenting the paper I co-authored with Chris Eliasmith on efficient navigation using a scalable, biologically inspired spatial representation. The main motivation for this work is taking the concept of a spatial semantic pointer and applying it as an encoding mechanism for spatial tasks trained through deep learning. We show in this paper how the biologically inspired SSPs offer many improvements over standard techniques used in the machine learning community. Let's start with a brief background on SSPs. SSPs utilize the concept of fractional binding to extend vector symbolic architectures to include continuous value signals in addition to discrete symbols. This is achieved through generalizing the circular convolution binding operator to non-integer powers, analogous to fractional exponents for multiplication. SSPs afford many useful properties, including the ability to represent multiple items in memory, easily shift the locations of items in memory, represent complex regions of space, and perform query operations on the memory to retrieve encoded items or their locations. A spatial semantic pointer remains fixed in size no matter how many objects are encoded or where those objects are located. In the example shown here, there are three objects which are each represented by an n-dimensional vector. The spatial semantic pointer for any xy location is also an n-dimensional vector. Each object can be bound to its location and summed together, the result being a memory vector, which is also still n-dimensional. One improvement to the SSP formulation that this paper introduces is defining the representation in terms of a hexagonal coordinate space. This idea is inspired by the hexagonal structure of grid cells and shows an improvement in the representation of 2D coordinates. Each heat map shown is formed by comparing the similarity of the representation for the 0, 0 coordinate with all other coordinates. There is a reduction in noise and other artifacts for the hexagonal formulation. Now on to the navigation task. The objective here is given your location, the location of a goal, and a contextual cue for which of many environments you are in, compute the optimal direction to move to get to the goal. The optimal policy is defined as one which requires the least distance traveled to reach the goal, while also avoiding being too close to the walls. Wall avoidance is achieved by adding a cost function based on proximity to a wall when solving for the shortest path. Neural networks are trained to solve this task, with all aspects of training held constant except for the spatial encoding function used. Each encoding transforms a 2D coordinate into a 256-dimensional vector. Each network is trained such that the same learned weights are used across multiple environment layouts with only the context input to distinguish them. The other encodings compared to are common methods for representing space used in machine learning tasks, such as Gaussian basis functions, tile coding, and one-hot encoding. Comparisons are also made for learning the encoding layer as well as directly using the 2D coordinates instead of any encoding. An additional baseline of random encodings is used to give an indication of worst-case performance. The SSP methods outperform all other methods, with the hexagonal formulation doing the best overall. While the effect size is relatively small in the first experiment, it becomes much greater when scaling is taken into account. In the experiment shown here, a larger environment is constructed by tiling together many smaller environments. SSPs do not require a specific limit to be set on the space they can represent. Most other methods require bounds to be set, where it is difficult to represent values outside of these bounds, and the larger the bounds, less accurate values within are represented. In contrast, SSPs can represent all locations equally well. The next experiment demonstrates how a complete navigation system can be created using spatial semantic pointers as the underlying representation. The task is as follows. Given an environment containing many known objects, navigate to a particular cued object using local sensor information. One component is the memory itself, along with a retrieval mechanism and a network to clean up a potentially noisy representation. Another component is a localization system, trained to map from a series of distance measurements around the agent to an SSP representing the current location. The final component is the policy network described earlier, which produces an action to move the agent towards the goal. Each time step, the output velocity from the policy is sent to the simulated world, causing the agent to move and receive new sensory data on the next time step. The result is goal-directed behavior based on the given cue. The same network can also be implemented fully through spiking neurons. Thanks for listening. If you are interested in learning more of the details, feel free to check out the paper or the accompanying code that is available online.